All right, just want to make a quick video to kind of go over some of the problems you're going to look at in Unit 7 because they have lots of different parts, so I just want to kind of make sure that we kind of know what's going on in each part. So we're going to be given a rational function, and a rational function is a function that has a top and a bottom that is each a polynomial. Now, the first thing I would do with all rational function problems is I would go ahead and factor the top and bottom. So I notice on the top that there is a 2 that I can take out of all of them. So that's going to become 2x squared plus x minus 2. And on the bottom, I'll just leave that the same. I can factor that eventually. What you want to make sure you do is you factor completely. Don't start canceling things out yet. You want to make sure that you have it completely factored first. So the top I could factor, two numbers that multiply to negative 2 add to positive 1 are going to be positive 2 and negative 1. And then on the bottom, two numbers that multiply to negative 5 but add to positive 4 are going to be positive 5 and negative 1. Now obviously you see that we have this factor that will cancel, but I don't want to cancel it quite yet. So we want to make sure that we do the domain before we cancel out, because the domain is going to be all reals except for what makes the bottom 0. So it can't be negative 5 and it can't be 1. Even though that x minus 1 cancels, that is still a domain restriction. So in interval notation, we're going negative infinity to negative 5, union negative 5 to 1, union 1 to infinity. So now that we have the domain, now I can cancel this out, and I can now think of this function as 2 times x plus 2 over x plus 5. So now I can think of the function as the simpler one where I have that factor of x minus 1 canceled. Now everything that's a domain restriction, these two things are either going to make a vertical asymptote or a hole. The thing that cancels out is going to make the hole, so in this case that's the 1. So there's going to be a hole at 1 comma something. Now, how do I find the y value of the hole? Well, I'm going to plug it into my now reduced function. I don't want to plug it into the original, because if I do, I'll get 0 over 0. But if I plug it into the new function, I get 2 times 1 plus 2 over 1 plus 5. So that's going to be 2 times 3 over 1 plus 5. That's going to be 6 over 6, which is just 1. So there's a hole at 1, 1. Sometimes I've done in the past, I'll always circle the one that cancels out because that one's going to be the hole, because whatever cancels out is going to make that hole. So I kind of make that hole symbol around it so I remember that. Now vertical asymptote is going to be the thing that makes the bottom 0 when it's in reduced form. In this case, that's just going to be x equal to negative 5. Remember, vertical asymptotes are always x equal, while horizontal and oblique are going to be y equal. Now the horizontal asymptote and the oblique asymptotes, that's the one that has all the rules, but the most typical example you'll see is when the power on the top and the power on the bottom are the same. And if they're the same, I just go back to my original and I take my highest power term on each side and I'll just divide that. So 2x squared divided by x squared is simply going to be 2. Now if the degree is bigger on the bottom, it is automatically 0. And if the degree on the top is bigger, then it is going to be some kind of oblique asymptote where you have to long divide. Now the x-intercept is when what's going to make the top equal to 0. Now the factor of 2 doesn't really matter, but the x plus 2 does, and negative 2 is what makes that 0, because negative 2 plus 2 is 0. The y-intercept, we can just plug in 0 for the x value. Now you can do this any place. You can do it in the original, you can do it in my final. It doesn't really matter. It does the same thing. But that's going to give me 4 over 5, so I'm going to get 0 and 4/5. Now with this information I can sketch my graph, because then it kind of talks about end behavior, what's happening as it approaches these asymptotes, things like that. So I'm going to kind of put a little graph there, and what I know is there is a vertical asymptote at negative 5. and I know there is a horizontal asymptote at 2. So my graph is going to follow these asymptotes, and I'm going to use the intercepts to kind of help me along the way. Now my y-intercept is 0, 4/5, so that's like a point there. And then my x-intercept is -2, 0. So pretty much I have everything graphed that I could ever have graphed from this information. Now you can use a graphing utility, or you can plot some more points, but the sketch of this graph is going to look something like this. So that's kind of an estimate of what it looks like. I know that this piece up here had to be in this box because there's no intercepts anywhere. And I knew this graph had to follow those two intercepts, and since it usually has this shape of these kind of two reciprocal curves, I kind of could imply that's where the graph was. So now if I want to do my end behavior, it says, where does this graph come from the left? So coming from the left side, you see this graph is going straight up, so it's going to be positive infinity. And as I come from the right side, so as my x's are coming from the right side, it's going down, so it's going to negative infinity. I could also say as x goes to infinity, as x goes to plus or minus infinity, the function actually goes to 2. Because you can see it is flattening out on both sides, so as you go to infinity, it's going to 2. But at that asymptote, that's where it's going to positive or negative infinity. So a lot of stuff happening in these problems, nothing really difficult mathematically, but it is difficult to kind of keep it all together. So hopefully this helps you out when you're working these problems.